Okay, so you sent us this research paper, and it's on Google's Chubby lock service.
Hmm.
And it's a fascinating look, I think, under the hood of a system that powers so many Google products that everyone uses probably every day.
Yeah.
And it might seem a little bit dense
Yeah.
at first glance, but trust me, there are some real aha moments in here.
Yeah.
Our deep dive today is to figure out not just what Chuggy does,
Hmm.
but why Google built it this way,
Right.
and what we can learn from its successes, its quirks, and even its little oops moments along the way.
Yeah, what's interesting is that it's not just about locks, even though that's in the name.
Right.
It's actually a surprisingly multifaceted service.
Okay, so unpack that for me.
Yeah.
What else does it do besides basic locking?
Well, you can think of it as a system for reliable storage of small files,
Okay.
a way to send notifications when things change,
Yeah.
and even a highly available name service, almost like a supercharged DNS.
So more robust than DNS. Why would they need that?
Exactly. The paper talks about how Google was dealing with these massive traffic spikes,
Okay.
and traditional DNS just wasn't cutting it.
Right.
Chubby's caching mechanism turned out to be much more efficient for handling these huge bursts of name lookups.
That makes sense. Handling that scale is a constant theme in this paper.
Mhm.
But I'm curious, why did they make Chubby a separate service?
Hmm?
Couldn't they have just incorporated this functionality as a library
Right.
that developers could include in their projects?
That's one of the design decisions they explicitly address.
Okay.
What's fascinating is they argue that a centralized service is actually better
Okay.
for real-world developer scenarios, especially at Google scale.
I can see how managing dependencies and updates across a vast organization
Right.
would be a nightmare if everyone was using their own slightly tweaked version of a lock library.
Yeah, exactly. And plus, by making it a service, they could ensure consistency
Okay.
and make it easier for developers to incorporate robust locking
Yep.
and other features without needing to be distributed systems experts.
Okay, so that explains the why behind the service-based approach. Now let's talk about those locks themselves.
Right.
The paper emphasizes that Chubby focuses on coarse-grained locking.
Yeah.
What exactly does that mean, and why did they choose that route?
It means Chubby is optimized for locks that are held for relatively long periods,
Okay.
as opposed to those super fast, short-lived locks you might see in other systems.
Okay.
Um, this was a deliberate decision with significant implications for performance and availability.
So if I'm understanding correctly, this means that Chubby is less about optimizing for tiny, frequent actions
Right.
and more about making sure that those crucial, long-held locks are
Yeah.
rock solid even if things go wrong.
Exactly. Think of it this way. If a Chubby server briefly goes down,
Yeah.
it's much less likely to affect applications that rely on those long-held locks.
Okay.
The system is designed to gracefully handle those brief disruptions.
That's a pretty clever way to build resilience into the system from the ground up.
Yeah.
But it also sounds like it might be a bit slower for those operations that do require quick locking and unlocking.
That's a trade-off they were willing to make. They prioritized the robustness and consistency of those critical long-held locks over raw speed for every single operation.
Right. It makes sense in the context of what they were trying to achieve.
Yeah.
So these coarse-grained locks are used to control access to what exactly? The paper mentions some familiar file system concepts like files, handles, and caching. But I'm guessing it's not as straightforward as a regular file system since we're dealing with a distributed setup.
You're right. Chubby borrows ideas from traditional file systems, but adapts them for a distributed world.
Okay.
For example, they talk about how the caching mechanisms are designed with consistency as the top priority, not just speed.
Okay.
They want to make absolutely sure that all clients have a unified view of the data, even if it means sacrificing a bit of performance in some cases.
Okay, so help me wrap my head around that. How do they ensure that consistency across all those different clients?
They use what's called explicit invalidations.
Okay.
Imagine the master server as a conductor orchestrating an orchestra.
Okay.
Whenever data is about to change,
Yeah.
it sends out signals to all the clients who might have cached that data,
Okay.
essentially saying, hey, your sheet music is outdated, get the latest version.
So it's a proactive way to prevent anyone from playing out of tune, so to speak.
Precisely. And to keep track of who's playing in the orchestra and whether they're still paying attention,
Right?
they use this concept of sessions and keep-alives.
Okay.
Think of it like the conductor making eye contact with each musician
Yeah.
to make sure they're still there and haven't wandered off for a coffee break.
Okay. This metaphor is working for me. So these keep lives are like a heartbeat
Exactly.
between the client and the master server.
Exactly. They ensure that the client session remains active and that both sides are in sync.
Oh.
And this gets really interesting when we start talking about what happens when a master server fails.
Ah, so that's where that grace period comes in that they mentioned.
So you got it. Even if a master server goes down, the clients have this window of time where they can reconnect to the new master without losing their session or any locks they're holding.
Right.
It's like a safety net built into the system.
That's essential for a system like this.
Right.
You can't have everything grinding to a halt just because one server hiccups.
Yeah.
But speaking of hiccups, the paper mentions this rather funny anecdote about how Google engineers themselves didn't always handle those failover events very gracefully in the early days.
Oh, yeah. It seems that some applications would simply crash when a master failover occurred.
Wow.
Instead of trying to reconnect and recover gracefully, they just give up. Imagine the chaos that caused.
Oh, no.
Yeah.
It's a good reminder that even the best laid plans can go awry, especially when you're dealing with the complexities of a distributed system. But it sounds like they learned from those early mistakes and made Chubby even more robust.
Yeah.
Now let's talk a bit about the database that powers Chubby.
Sure.
In the beginning, they used Berkeley DB, a well-established database system.
Yeah.
But they eventually decided to move to a custom-built database that was simpler and more tailored to Chubby's specific needs.
Right.
Why the switch was Berkeley DB not powerful enough?
It wasn't about power. They actually found that Berkeley DB, while robust, was a bit too much for what Chubby needed. Its replication features weren't quite mature enough at the time, and they realized they could streamline things considerably with a custom solution.
So it's like they traded a Swiss Army knife for a really well-crafted, specialized tool.
That's a great way to put it.
Okay.
They gained more control and could optimize the database specifically for Chubby's workload.
Right.
Which makes a lot of sense when you're dealing with a service as critical as this.
Absolutely. Now, one of the things that really stood out to me in this paper
was how they tackled the challenges of mirroring and scaling.
Yeah.
We're talking about a system that needs to handle Google's immense load. So those are not trivial problems.
Right. You're right. And their approach to these challenges is fascinating.
Okay, so walk me through it.
Okay.
How did they make Chubby both robust and scalable?
Well, for mirroring, they have a system where changes in one Chubby cell, think of it like a regional data center, can be quickly replicated to cells all over the world. This is vital for keeping things like configuration files consistent across multiple locations.
Right.
They even have this special global cell that acts as the source for mirrored data. Ensuring critical information is always accessible.
So it's like having a backup orchestra ready to step in if the main one has a power outage?
Yeah, and for scaling, they use a multi-pronged approach.
Okay.
First, they can just create more Chubby cells as needed,
okay,
keeping the load distributed and manageable.
Second, they have these clever techniques where the master server can dynamically adjust the lease times for client sessions.
Hold on, back up a bit.
Yeah.
What do you mean by lease times?
Remember those keep alive messages we talked about?
Yes.
Well, the lease time is essentially how long a client has before it needs to send another keep alive message to refresh its session. By tweaking these lease times on the fly, the master server can reduce the frequency of those messages when things get busy, freeing up resources.
So it's like the conductor giving the musicians a longer break between those eye contact check-ins when the music gets really intense.
Exactly. And then, of course, they rely heavily on client-side caching to further reduce the number of requests hitting the server.
So it's like having everyone memorize their parts as much as possible so they don't need to keep checking the sheet music.
Exactly.
Okay.
All of these techniques work together to make Chubby incredibly robust and able to scale to handle Google's immense demands.
It's a remarkable feat of engineering, but the paper is also refreshingly honest about some of the things that didn't go as planned. They openly discuss some of the design errors and surprises they encountered along the way.
And that's one of the things I appreciate most about this paper. They don't shy away from admitting their mistakes.
Right.
Which makes the whole thing feel much more relatable and human.
Okay, spill the beans. What kind of design errors did they run into?
Okay.
I'm sure there's some good stories there.
Well, one that comes to mind is their initial struggle with Java clients.
Oh, interesting.
Remember, Google's infrastructure is heavily reliant on C++. So introducing Java into the mix created some unforeseen complications.
Interesting. Why was Java a problem for Chubby?
It boiled down to those fundamental differences in design philosophies.
Okay.
Java prioritizes portability, and that didn't play well with Chubby's C++-centric design.
Okay.
They considered using Java Native Interface, JNI, but that was deemed too slow.
Yeah.
In the end, they had to create a special protocol conversion server to bridge the gap between Java clients and the Chubby service.
So they essentially had to build this extra layer just to accommodate Java?
Right.
That's quite a workaround.
It highlights the complexities of managing a diverse ecosystem and those trade-offs you sometimes have to make in the real world.
Okay. What other surprises did they encounter?
One of the things they discuss is the challenge of dealing with what they call abusive clients.
Okay.
And before you think we're talking about hackers, they're actually referring to well-intentioned developers who unintentionally put excessive strain on the system due to certain coding patterns.
So it's more about misuse than malicious intent.
Exactly. And they admit that they didn't always anticipate these issues early on.
Okay.
For example, they underestimated the importance of caching the absence of files.
Why was that so important?
Well, developers often write code that repeatedly tries to open a file, even if it doesn't exist. It's a common pattern.
Yeah.
But without caching those file not found responses, each attempt triggers a request to the server, which can quickly add up, especially at Google scale.
Ah, so it's like those persistent telemarketers who keep calling.
Exactly.
Even after you've told them you're not interested.
Right.
Except in this case, it's code, not salespeople. That's being annoying.
That's a great analogy. And they initially tried to discourage this by introducing increasing delays for repeat attempts. But it actually revealed underlying bugs in some cases.
So they inadvertently helped improve code quality by making those issues more visible.
You could say that, but ultimately they found the most pragmatic solution was to just make those repeated open calls less expensive on the server side.
Sometimes the simplest solution is the best.
They also found that developers weren't always aware of the performance costs associated with certain Chubby operations. They hadn't provided enough guidance in their documentation, assuming that developers would intuitively understand those costs.
Yeah, it's easy to get caught up in the functionality of a system and overlook those performance nuances, especially when you're focused on solving a specific problem.
Right. And one of the examples they give is this module, initially designed to track data uploads for a small group of users. They stored some metadata in Chubby, which seemed fine at first. But as other services adopted this module, the infrequent uploads turned into a constant stream of data, putting a huge strain on Chubby.
So it was a classic case of a seemingly harmless use case scaling up to become a major issue?
Exactly. It highlighted the importance of anticipating how a system might be used in unexpected ways and the need to design for those potential growth scenarios. They also had to contend with developers trying to use Chubby in ways it was never intended for, like trying to turn it into a full-blown publish-subscribe system.
That's a familiar problem.
Yeah.
It's like using a hammer to try to screw in a light bulb.
Exactly. They realized they needed to be more proactive in educating developers about the appropriate use cases for Chubby and the potential pitfalls of trying to stretch it beyond its limits.
So it's about setting those boundaries and saying, here's what Chubby excels at, but for these other things, you should probably use a different tool.
Right. And they also learned that seemingly minor API design choices could subtly influence how developers dealt with outages.
Oh, okay.
Remember that master failover event we talked about earlier?
Yes.
The one that caused some applications to crash instead of gracefully recovering?
Yeah, it's hard to believe something as simple as an API design choice could have that much impact.
It's a reminder that even those small details can ripple outward and affect the overall system's behavior.
It seems like they really uncovered a lot about the complexities of building distributed systems at Google scale.
They did. And in the next part of our deep dive, we'll explore some of the key lessons they learned and the insights they gleaned from these experiences.
I'm looking forward to it. This is turning out to be a much more fascinating deep dive than I initially expected.
Me too. It's not just about the technical details. It's about understanding the human element of system design and those unintended consequences that can arise even from the best intentions.
Okay, so we've explored like the nuts and bolts of Chubby, its design choices, and some of those unexpected challenges they ran into. Now let's shift gears and talk about what they learned from all of this.
Right.
The paper goes into some detail about like those broader lessons, right?
They do. And what's really interesting is that many of these lessons go beyond the technical specifics of Chubby and speak to the challenges of building any large-scale distributed system.
Okay, give me an example. What kind of insights are we talking about?
One recurring theme is that developers often underestimate the importance of availability.
Right.
They tend to assume that services like Chubby will always be there, ready to respond to their requests. But in a distributed world, that's just not realistic.
I can see how that mindset might creep in, especially when you're like so focused on the specific task at hand.
Exactly. But they learn the hard way that even brief outages, while hopefully infrequent, can still happen, and systems need to be designed to handle those disruptions gracefully.
So it's not enough to just like build a highly available service.
Right.
You also need to design your systems in a way that minimizes the impact of those inevitable disruptions on the client side.
Yeah, they call this designing for resilience and graceful degradation.
Makes sense. Now, they also talk about the importance of understanding the interplay between human factors and technical design decisions.
Yeah.
What exactly do they mean by that?
Well, they realize that seemingly minor choices, like how they designed a particular API or how they worded their documentation, could have a huge impact on how developers used or misused the system.
Right.
It was all about anticipating those potential pitfalls
Right.
and trying to nudge developers toward those best practices that would ensure the overall reliability and scalability of the system.
So it sounds like they were constantly trying to anticipate how developers might interact with the system and design it in a way that made those positive interactions more likely.
That's a great way to put it, that they talk about those unintended consequences that can arise even from the best intentions. For instance, remember that event notification for master failover that we talked about earlier?
Yes.
The one that caused some applications to crash instead of gracefully recovering?
Yes. It's still surprising to me that something as simple as an API design choice could have that much impact.
It's a perfect example of what they're talking about.
Okay.
They intended for that event to be helpful, a way for clients to check for potential data changes after a failover.
Right.
But many developers took the easy way out and simply crashed their applications upon receiving it.
Oh, wow.
Making their systems more fragile rather than more robust.
So it's like hitting the panic button when the fire alarm goes off.
Exactly. It highlights the need to think carefully about how your design decisions might influence developer behavior and to try to anticipate those potential pitfalls.
All right. So designing for resilience, understanding human factors. What other key lessons did they emphasize?
They also learned the importance of constantly reflecting on their design choices. And being open to refining them as they learn more about how the system was used in practice.
So it was a process of continuous improvement, constantly seeking ways to make Chubby better based on real-world feedback.
Exactly. They emphasize that you can't just build a system and walk away.
Right.
You need to monitor it, gather data, and be willing to adapt as you learn more about how it's being used.
Now, they also talk about understanding those low-level technical details. Even if you're working at a higher level of abstraction, why should developers care about those lower-level details?
Well, remember how they had to use UDP for keep alive messages?
Yes.
Because of TCP's behavior during network congestion.
Yes. It was a reminder that those fundamental protocol limitations can force you to make design compromises at a higher level.
Exactly. And they argue that having a deeper understanding of those lower-level constraints can help you make more informed decisions when designing distributed systems.
It's like knowing how the engine works can help you drive a car more efficiently, even if you don't need to be a mechanic.
That's a great analogy. They also spent a lot of time comparing Chubby to other systems, particularly Boxwood's lock service.
Right. I was curious about that comparison. Why did they choose Boxwood specifically?
Because, like, Chubby Boxwood was designed for a loosely coupled distributed environment. But it took a different approach, a more modular one. It's like comparing a Swiss Army knife to a set of individual specialized tools.
So Chubby is the Swiss Army knife in this scenario.
Exactly. It provides a more unified and integrated solution with features like a shared namespace for locks and files, automatic client-side caching, and those helpful event notifications.
So it's designed to be easier to use, especially for developers who might not be distributed systems experts.
That's a key part of their design philosophy.
Yeah.
They wanted to make it as straightforward as possible
Okay.
for developers to incorporate Chubby into their applications without needing to worry about the nitty-gritty details.
Whereas Boxwood is more like a toolbox that allows developers to pick and choose the components they need.
Right, and that approach makes sense for their intended audience, which was likely a smaller group of more specialized developers working on projects that might share common building blocks but didn't need to be as tightly integrated.
It's fascinating to see how those different design philosophies led to systems that, while addressing similar challenges, have such distinct architectures.
Yeah, it highlights the importance of understanding the specific needs of your target audience and the trade-offs involved in choosing one approach over another.
Now, another key point of comparison is how they handle the concept of a grace period. Oh, right. I remember them mentioning that. Didn't they say that Boxwood's grace period is more like Chubby's session lease?
Exactly. And Chubby, the grace period is all about giving clients that extra time to recover after a master failover.
Right.
It's like an insurance policy that ensures they don't lose their sessions or any held locks, even if the master server is down for an extended period.
So it's a more robust mechanism designed to handle those potentially disruptive events.
Right. In Boxwood, the so-called grace period is more about defining the expected duration of a session.
Okay.
Rather than providing that extended window for recovery during a failover.
Okay, so it's like a promise from the master server saying, I won't unilaterally terminate your session within this time frame.
Right.
But after that, it's up for grabs.
That's a great way to summarize it. And this difference reflects the varying assumptions about scale and failure probability in the two systems. Chubby, designed for Google's massive scale, anticipates those potential disruptions and builds in that extra layer of protection.
Makes sense. Now, they also mentioned that Chubby's locks are designed to be heavier weight than those in Boxwood. What did they mean by that?
It's all about what those locks are designed to protect.
Okay.
Chubby's locks are capable of protecting not just individual files, but also external resources that might depend on those files.
So it's not just about coordinating access to data within Chubby itself. It's about synchronizing actions across a whole ecosystem of interconnected components.
Exactly. And they even introduced those sequencers to ensure that operations on those external resources happen in the right order, preventing conflicts and maintaining consistency.
Okay, that makes sense. But with all this talk about locks and files and consistency, I almost forgot that one of Chubby's most popular uses is as a name service. They even admitted that they didn't anticipate this becoming such a dominant use case.
It's true. They designed Chubby as a robust lock service. And it ended up revolutionizing how Google handles name resolution.
What is it about Chubby that makes it such a good fit for a name service?
Well, a lot of it comes down to that efficient caching mechanism we talked about earlier.
Right.
Traditional DNS relies on time-based caching, which means that entries expire after a certain period and need to be constantly refreshed.
Right.
This works fine in many cases, but it can put a huge strain on the system when you're dealing with Google's scale.
So those constant refresh requests can become a bottleneck.
Exactly.
Especially during those peak traffic periods.
Right. But Chubby, with its explicit invalidations, can handle those huge numbers of clients and frequent changes much more efficiently.
Okay.
Client caches only need to be updated when something actually changes, not on some arbitrary schedule.
So it's a much more dynamic and responsive approach to caching.
You got it. And the paper gives this great example of how Chubby's caching outperformed traditional DNS when handling name resolution for those massive jobs involving thousands of processes. They calculated that with DNS, a single job with just 3,000 clients could require over 150,000 lookups per second just to maintain the caches.
That's a mind-boggling number of requests. No wonder they ran into scalability problems with DNS.
Exactly. And this ability to provide those rapid name updates without relying on constant polling was so appealing that Chubby gradually became Google's primary internal name service, replacing DNS for many critical applications.
So it was almost an accidental revolution?
Yeah.
They stumbled upon a solution that addressed a major pain point, and it spread throughout the organization.
It's a classic example of how a well-designed system can find unexpected applications beyond its original intended purpose.
It makes me wonder if they ever, patted themselves on the back for accidentally building something. That solved a problem they didn't even know they had.
I'm sure they did. But even with Chubby's superior caching, they still had to contend with those occasional load spikes, especially when large jobs were starting up and generating millions of name resolution requests simultaneously.
So what did they do to mitigate those traffic bursts?
Well, they cleverly decided to group name entries into batches.
Okay.
This allowed them to return multiple name mappings with a single lookup, significantly reducing the number of requests during those critical startup phases.
It's amazing how those seemingly small optimizations can have a big impact on performance.
It's true. They also point out that Chubby's caching semantics, while great for consistency, are actually more strict than what's strictly needed for name resolution.
So in a sense, they were over-engineering the solution for this particular use case.
You could say that they even suggest that they could have further reduced the load on Chubby by introducing a simplified protocol conversion server specifically designed for name lookups. One that didn't enforce those strict consistency guarantees.
So it's like using a sledgehammer to crack a nut.
Exactly.
Albeit a very large and important nut.
Exactly. But remember, they didn't initially anticipate this heavy reliance on Chubby as a name service.
Right.
It emerged organically as developers discovered its benefits.
It's a testament to the flexibility and power of the system they built.
It is. And to bridge the gap between the Chubby world and those systems still reliant on traditional DNS, they even created a Chubby DNS server.
Okay.
This server acts as a translator, making the naming data stored within Chubby accessible to those DNS-dependent clients.
So it's like a compatibility layer that allows them to gradually transition away from DNS without disrupting existing applications?
Precisely. It's a reminder that successful system design is often as much about understanding the social and organizational context as it is about those technical details.
That's a great point. And speaking of the human element, let's revisit those abusive clients they mentioned.
Right.
They devote a surprising amount of space in the paper.
They do.
To discussing these unintentional troublemakers.
They do. And for good reason, these weren't malicious actors deliberately trying to take down the system. They were well-intentioned developers who, due to certain coding practices or misunderstandings about Chubby's behavior, ended up putting excessive strain on the service.
So it was more about well-intentioned but perhaps not fully informed users who pushed the system beyond its limits.
Exactly. And the authors are surprisingly candid about their own early missteps in anticipating and mitigating these issues. They admit that their initial reviews of how project teams planned to use Chubby weren't always thorough enough.
So even the Chubby experts themselves fell victim to those blind spots. It makes them seem much more human and relatable.
Right.
What kind of problems did they encounter with these abusive clients?
Well, one example they highlight is the lack of aggressive caching in the early versions of Chubby.
Okay.
Remember, client-side caching is crucial for reducing the load on the server, especially when you have a large number of clients.
Yeah, right.
But they initially underestimated the importance of caching not just file data, but also the absence of files.
Why was caching file absence so important?
Well, it turns out that developers often write code that repeatedly tries to open a file, even if it doesn't exist. It's a common pattern for handling scenarios where a file might be created asynchronously or where you need to poll for its existence.
I see. So if you're not caching that file not found response, those repeated attempts can lead to a lot of unnecessary requests to the server.
Precisely. And initially, they tried to address this by introducing those exponentially increasing delays for repeated attempts to open the same file. They hoped this would nudge developers to fix their code. But in some cases, it actually revealed underlying bugs that the developers hadn't even realized were there.
So they inadvertently helped improve the overall code quality by highlighting those hidden issues.
You could say that, but ultimately they found that the most pragmatic solution was simply to make these repeated open calls less expensive. It was easier to optimize the system than to try to change developer behavior overnight.
Sometimes the most elegant solution is the one that requires the least amount of friction.
Right. And they also point out that they didn't initially provide much performance guidance in their documentation. They assumed, perhaps naively, that developers would intuitively understand the costs associated with various Chubby operations. But in reality, developers often focus on functionality first and performance later.
It's easy to get caught up in the what of a system and overlook the how until you start hitting those performance bottlenecks.
Absolutely. And they learned that lesson the hard way.
Okay.
They give an example of a module that was initially designed to track data uploads for a small group of users, storing some metadata in Chubby. This seemed fine at first, as those uploads were infrequent and restricted to a small group of users. But then other services started using the same module to track uploads from a much wider user base.
Oh, I can see where this is going.
Right as those services grew, so did their Chubby usage. It got to the point where a single large file was being rewritten in its entirety for every user action.
Oh, no.
And the total space consumed by these services dwarfed the combined usage of all other Chubby clients.
That's a classic example of how seemingly innocent use cases can spiral out of control.
Absolutely. They eventually had to step in and introduce a file size limit and encourage those services to migrate their data to more suitable storage systems. But as you can imagine, getting those changes implemented in busy production systems took time and effort.
Right.
It was a valuable lesson in the importance of planning for unexpected growth in usage patterns.
It sounds like they learned a lot about the unpredictable nature of developers.
They did.
And the importance of anticipating how a system might be used or misused.
They did. And they also had to contend with developers trying to use Chubby in ways it was never designed for.
Right.
Like attempting to turn it into a full-blown publish-subscribe system.
Right. Those well-intentioned but misguided attempts to repurpose a tool for something beyond its intended scope.
Exactly. They learned that they needed to be more proactive in educating developers about the appropriate use cases for Chubby and the potential pitfalls of trying to stretch it beyond its limits.
So it's about setting those boundaries and saying, this is what Chubby is great for, but here are some things you should probably use a different tool for.
Right. And they also realized that certain API choices could inadvertently encourage developers to make assumptions about Chubby's availability that weren't always realistic. Remember that event notification for master failover that we talked about earlier?
Here. The one that caused some applications to crash instead of gracefully recovering.
That's the one.
Okay.
While they intended for that event to prompt clients to check for potential data changes, many developers simply crashed their applications upon receiving this event.
Wow. So instead of building in robustness, they made their applications more fragile.
Ironically, yes. They realized that they might have been better off sending redundant file change events or even ensuring that no events were lost during a failover.
Right.
It highlights how seemingly minor API design decisions can have ripple effects on how developers use and misuse a system.
So it's all about understanding those human factors.
Absolutely. And they also had to contend with situations where even though a Chubby cell was technically up and running, it might not be truly available to all clients due to network issues, routing problems, or even planned maintenance events.
So it's not just about ensuring that the service itself is highly available. It's also about recognizing that the perceived availability from the client's perspective might be different due to those external factors.
Precisely. And they had to constantly remind developers that even those brief Chubby outages, while infrequent, could still happen. And their systems needed to be designed to handle those disruptions gracefully.
So it was a constant battle to balance those expectations of high availability with the realities of operating in a distributed environment.
Indeed. And they also learned that seemingly minor decisions, like how they handled the cancellation of long-running calls, could have unintended consequences for how developers structured their code.
Right. They mentioned that their initial approach of discarding all server-side state upon cancellation made it difficult to share handles between multiple threads, limiting flexibility.
Exactly. And they suggest that they should have added a dedicated cancel RPC that would allow for more flexible sharing of open handles without those unwanted side effects.
So even those seemingly minor details can matter?
They do.
Okay.
It's a reminder that even seemingly minor details in an API can have consequences for how developers structure their code.
It sounds like they gained valuable insights into the interplay between system design and developer behavior.
They certainly did. And they also learned that their use of keep alive messages for both session management and event notification created some interesting challenges with those underlying transport protocols.
Oh, right. They mentioned having to use UDP for keep alives because of TCP's behavior during network congestion. Didn't they prefer to use TCP whenever possible?
They did, but here's the thing. Keep alive served a dual purpose.
Okay.
They were used to refresh a client's session lease and to deliver events and cache invalidations from the master server to the client.
Right.
This design had the benefit of ensuring that clients couldn't refresh their sessions without acknowledging those invalidations, which was good for consistency.
I see. So it was an elegant solution in theory, but it ran into practical issues because of TCP.
Exactly. TCP's congestion control mechanisms, while great for reliable data transfer, weren't well suited to the time-sensitive nature of Chubby's lease management. During periods of network congestion, TCP's back-off policies could cause keep-alive messages to be delayed, potentially leading to lost sessions.
Ah, that makes sense. Those keep-alive messages needed to get through promptly to maintain those sessions.
Precisely. So they reluctantly switched to UDP for keep-alives, since UDP doesn't have those congestion control mechanisms and is generally more responsive. But it wasn't their ideal solution, as they acknowledged that UDP. They did acknowledge that UDP should be used sparingly, primarily for situations where you have strict time bounds. But they were stuck between a rock and a hard place in this particular situation.
So it sounds like a classic engineering trade-off. What did they propose as a potential solution to reconcile those conflicting needs?
Well, they suggested adding a separate TCP-based mechanism specifically for handling those events and invalidations. They called it GET event. This would allow them to use TCP for the bulk of their communication, which they generally preferred for its reliability, while still maintaining those timely session renewals over UDP.
Ah, so essentially decoupling those two functions that were originally combined in the keep alive messages, divide and conquer.
Exactly. And it's a great illustration of how those seemingly simple design choices can have these unexpected implications and sometimes require creative workarounds to reconcile practical constraints with your design goals.
It's a good reminder that there's often no single perfect solution. It's all about navigating those trade-offs and finding the best fit for your particular context.
Couldn't have said it better myself. And speaking of context, I think one of the most valuable aspects of this paper is their in-depth comparison of Chubby to other systems, especially Boxwood's lock service.
I was hoping we'd get to that. It's like comparing notes from two different teams who set out to solve a similar problem, but maybe with different philosophies or priorities.
Exactly. And one of the key takeaways for me is that both systems were designed with different target audiences and use cases in mind. Chubby, as we've been discussing, was built for this incredibly broad and diverse audience at Google, ranging from those seasoned distributed systems gurus to folks who are just starting out with this kind of technology.
So they needed a system that was powerful and could handle Google's scale, but also something that wasn't going to scare away developers who weren't necessarily experts in distributed systems.
Right, and that's reflected in Chubby's design. It provides a much higher level interface than Boxwood, with features like that unified namespace for locks and files, the automatic client-side caching we discussed, and those helpful event notifications. They really wanted to make it as straightforward as possible for developers to use, even if they weren't steeped in the intricacies of distributed systems.
It's like they tried to anticipate those common pitfalls and provide those guardrails to keep developers on the right track.
Exactly. Now, Boxwood, on the other hand, takes a more modular approach. It separates out those core functionalities like locking reliable state storage using a protocol called Paxos and failure detection into these distinct components. This gives developers more flexibility to pick and choose the pieces they need and even potentially use them independently.
Hold on, you mentioned Paxos. For those of us who aren't familiar with that, can you give us a quick explanation of what that is?
Of course, Paxos is a type of distributed consensus algorithm. It's a way for multiple computers to agree on a single value, even if some of those computers fail or there are network disruptions. It's a fundamental building block for ensuring consistency in distributed systems.
Okay, that makes sense. So Boxwood, with its modular approach, is more like a set of specialized tools, whereas Chubby is more like that all-in-one solution.
That's a great way to think about it. And that modularity makes sense for Boxwood's intended audience, which was likely a smaller group of more specialized developers working on projects that might have shared some building blocks, but didn't necessarily need that tight integration that Chubby provides.
It's fascinating to see how those different philosophies led to systems that, while tackling similar problems, ended up with such different architectures. But ultimately, they both had to grapple with those same fundamental challenges of distributed systems, like ensuring consistency, handling failover, and scaling to handle large numbers of clients.
Exactly. It's like they were both exploring different points on the design spectrum, each with its own strengths and trade-offs.
You know, it's funny, with all this talk about locks and consistency and failover, I almost forgot that one of Chubby's most popular uses is as a name service. They even say in the paper that they didn't anticipate this becoming such a dominant use case.
It is a bit ironic, isn't it? They set out to build this robust lock service, and it ends up changing the way Google does name resolution. It turns out that Chubby's caching mechanism is a perfect fit for a name service, especially when you compare it to the traditional approach used in DNS, the domain name system.
Okay, remind me, what's the big difference between how Chubby handles caching versus DNS?
Well, DNS relies on time-based caching. Each DNS record has a time to live, or TTL value, and after that time expires, the record is considered stale and needs to be refreshed. This works well in many cases, but if you need really fast updates or you have a ton of clients constantly querying for names, it can put a significant strain on those DNS servers.
Ah, so it's that constant need to refresh entries that can lead to overload, especially when you're dealing with Google scale. Like, I can see how that would be a problem.
Right. Now, Chubby takes a different approach. It uses explicit invalidations to manage its cache. This means that client caches can hold on to entries indefinitely, only refreshing them when they receive a specific invalidation message from the master server.
So it's a much more efficient way to keep those caches up to date, especially when you have lots of clients and frequent changes.
Exactly. And this advantage became really apparent when Google started using Chubby to handle name resolution for these massive jobs involving thousands of processes. The paper mentions that with traditional DNS, maintaining the caches for a single job with just 3,000 clients could require over 150,000 lookups per second.
Wow, that's a crazy number of requests. No wonder they ran into scaling problems with DNS.
Exactly. But with Chubby's invalidation-based caching, they could handle a significantly larger number of clients without overwhelming the system. The master server only needs to send out those invalidation messages when something changes, rather than constantly responding to refresh requests.
It's a much more elegant solution for those dynamic environments where things are constantly changing.
Precisely. And this ability to provide those swift name updates without relying on polling each name individually proved to be so appealing that Chubby gradually became Google's primary internal name service, replacing DNS for many critical applications.
So it was almost an accidental revolution. They stumbled upon a solution that addressed a major pain point, and it quickly spread throughout the organization.
In a way, yes. It's a great example of how a well-designed system can solve problems you didn't even know you had. But even with Chubby's superior caching, they still had to deal with those occasional load spikes, especially when large jobs were starting up and generating millions of name resolution requests simultaneously.
So how did they tackle those bursts of traffic?
Well, they came up with a clever solution. They decided to group name entries into batches. This allowed them to return multiple name mappings with a single lookup, significantly reducing the number of requests needed during those critical startup phases.
That's a great example of how even seemingly minor optimizations can have a significant impact on performance, especially at scale.
It's true. And they also acknowledge that Chubby's caching semantics, while perfect for ensuring consistency, are actually more strict than what's strictly needed for name resolution. They point out that for name lookups, timely notification of changes is often sufficient. You don't always need that absolute guarantee of consistency that Chubby provides.
So in a sense, they were over-engineering the solution for this particular use case.
You could say that. And they even suggest that they could have potentially reduced the load on Chubby even further by introducing a simple protocol conversion server specifically designed for name lookups. This server could have handled those less strict consistency requirements more efficiently.
So it's like they were using a sledgehammer to crack a nut, albeit a very large and important nut.
Exactly. But remember, they didn't initially anticipate this heavy reliance on Chubby as a name service. It emerged organically as developers discovered its benefits.
It's a testament to the power of a well-designed system that it can find unexpected applications beyond its original intended purpose.
Absolutely. And to further bridge the gap between the Chubby world and the traditional DNS world, they even created a Chubby DNS server. This server acts as a translator, making the naming data stored within Chubby accessible to those clients that still rely on DNS.
So it's like a compatibility layer that allows them to gradually transition away from DNS without disrupting existing applications.
Precisely. It's all about providing those smooth migration paths and recognizing that you can't always force everyone to adopt a new technology overnight.
It's a great reminder that successful system design is often as much about understanding the social and organizational context as it is about the technical details.
It really is. Now, one of the recurring themes in this paper is the challenge of dealing with what they call abusive clients. These aren't malicious actors trying to take down the system, but rather those well-intentioned developers who, due to certain coding practices or misunderstandings about Chubby's behavior, inadvertently put excessive strain on the service.
Right. They talked about that earlier, and it seemed like they learned a lot from those experiences. Can you give me some more specific examples of the kinds of issues they encounter with these abusive clients?
Of course, one example they highlight is the lack of aggressive caching in the early versions of Chubby. Remember, client-side caching is crucial for reducing the load on the server, especially when you have a large number of clients. But they initially underestimated the importance of caching, not just the file data, but also the absence of files.
Why was caching file absence so important?
Well, it turns out that developers often write code that repeatedly tries to open a file, even if it doesn't exist. It's a common pattern for handling scenarios where a file might be created asynchronously or where you need to pull for its existence.
I see. So if you're not caching that file not found response, each of those attempts triggers a request to the server, which can add up quickly.
Exactly. And they initially tried to address this by introducing those exponentially increasing delays for repeated attempts to open the same file. Their hope was that this would encourage developers to fix their code. But in some cases, it actually exposed underlying bugs that the developers hadn't even realized were there.
So their attempt to discourage a certain behavior actually led to the discovery of other issues?
It's a reminder that sometimes the solutions you implement can have unintended consequences. Ultimately, they found that the most effective solution was simply to make those repeated open calls less expensive on the server side. It was easier to optimize the system than to try to change developer behavior overnight.
Sometimes the most pragmatic solution is the best.
And they also found that developers weren't always aware of the performance costs associated with certain Chubby operations. They hadn't provided enough guidance in their documentation, assuming that developers would intuitively understand those costs.
It's easy to get caught up in the functionality of a system and overlook those performance nuances, especially when you're focused on solving a specific problem.
Right. And they give an example of a module that was initially designed to track data uploads for a small group of users storing some metadata in Chubby. This seemed fine at first, as those uploads were infrequent and restricted to a small group of users. But then other services started using the same module to track uploads from a much wider user base.
I see where this is going.
As those services grew, so did their Chubby usage. It got to the point where a single large file was being rewritten in its entirety for every user action. And the total space consumed by these services dwarfed the combined usage of all other Chubby clients.
That's a classic example of how seemingly innocent use cases can spiral out of control.
Absolutely. They eventually had to step in and introduce a file size limit and encourage those services to migrate their data to more suitable storage systems. But as you can imagine, getting those changes implemented in busy production systems took time and effort. It was a valuable lesson in the importance of planning for unexpected growth and usage patterns.
It sounds like they learned a lot about the unpredictable nature of developers and the importance of anticipating how a system might be used or misused.
They did, and they also had to contend with developers trying to use Chubby in ways it was never designed for, like attempting to turn it into a full-blown publish-subscribe system.
Oh yes, those well-intentioned but misguided attempts to repurpose a tool for something beyond its intended scope.
Exactly. They learned that they needed to be more proactive in educating developers about the appropriate use cases for Chubby and the potential pitfalls of trying to stretch it beyond its limits.
It's like setting those boundaries and saying, this is what Chubby is great for, but here are some things you should probably use a different tool for.
Right. And they also realized that certain API choices could inadvertently encourage developers to make assumptions about Chubby's availability that weren't always realistic. Remember that event notification for master failover that we talked about earlier?
The one that caused some applications to crash instead of gracefully recovering.
That's the one. While they intended for that event to prompt clients to check for potential data changes, many developers simply crashed their applications upon receiving this event.
So instead of building in robustness, they made their applications more fragile.
Ironically, yes. They realized that they might have been better off sending redundant file change events, or even ensuring that no events were lost during a failover. It highlights how seemingly minor API design decisions can have ripple effects on how developers use and misuse a system.
It's all about understanding those human factors.
Absolutely. And they also had to contend with situations where even though a Chubby cell was technically up and running, it might not be truly available to all clients due to network issues, routing problems, or even planned maintenance events.
So it's not just about ensuring that the service itself is highly available. It's also about recognizing that the perceived availability from the client's perspective might be different due to those external factors.
Precisely. And they had to constantly remind developers that even those brief Chubby outages, while infrequent, could still happen. And their systems needed to be designed to handle those disruptions gracefully.
So it was a constant battle to balance those expectations of high availability with the realities of operating in a distributed environment.
Indeed. And they also learned that seemingly minor decisions like how they handled the cancellation of long-running calls could have unintended consequences for how developers structured their code.
Right. They mentioned that their initial approach of discarding all server-side state upon cancellation made it difficult to share handles between multiple threads, limiting flexibility.
Exactly. They now suggest that they should have added a dedicated cancel RPC that would allow for more flexible sharing of open handles without those unwanted side effects. It's a reminder that even seemingly minor details in an API can have consequences for how developers structure their code.
It sounds like they gained valuable insights into the interplay between system design and developer behavior.
They certainly did. And they also learned that their use of keep alive messages for both session management and event notification created some interesting challenges with those underlying transport protocols.
Oh, right. They mentioned having to use UDP for keep alives because of TCP's behavior during network congestion. Didn't they prefer to use TCP whenever possible?
They did. But the problem was that those keep alive messages were serving a dual purpose. They were being used to both refresh a client's session lease and to deliver events and cache invalidations from the master server to the client. This design had the benefit of ensuring that clients couldn't refresh their sessions without acknowledging those invalidations, which was good for consistency.
So it was an elegant solution in theory, but it ran into practical issues because of the way TCP behaves.
Exactly. TCP's congestion control mechanisms, while great for reliable data transfer, weren't well suited to the time-sensitive nature of Chubby's lease management. During periods of network congestion, TCP's back-off policies could cause those keep alive messages to be delayed, potentially leading to lost sessions.
That makes sense. Those keep alive messages needed to get through promptly to maintain those sessions.
Precisely. So somewhat reluctantly, they ended up switching to UDP for those keep alives, since UDP doesn't have those congestion control mechanisms and is generally more responsive. But it wasn't their ideal solution, as they acknowledged that UDP should be used sparingly, primarily for those situations where you have strict time bounds.
So yet another trade-off. What did they propose as a potential way to reconcile those conflicting needs?
They suggested adding a separate TCP-based mechanism specifically for handling those events and invalidations, calling it getEvent. This would let them use TCP, which they preferred for most of their communication, while still maintaining timely session renewals over UDP.
So essentially separating those two functions that were originally combined in the keep alive messages.
Precisely. It's a great example of how even those seemingly simple design decisions can have unintended consequences, requiring creative workarounds to reconcile practical limitations with your design goals.
It seems like building a system like Chubby is a bit like playing a game of whack-a-mole. You solve one problem and another one pops up somewhere else.
That's a great analogy, and that's what makes it such a fascinating challenge.
So after tackling all these challenges and learning from their experiences, what were some of the key takeaways they highlighted?
Well, one recurring theme is this idea that developers often don't think enough about availability.
Right. They tend to assume that services like Chubby will always be there, ready to respond to their requests, but in a distributed world, that's just not realistic.
Exactly. And they emphasize that it's not enough to simply build a highly available service. You also need to design your systems in a way that minimizes the impact of those inevitable disruptions.
So it's all about building in resilience and graceful degradation.
Absolutely. And they also point to the importance of understanding the interplay between those human factors and technical design decisions.
What do you mean by that?
Well, they realize that seemingly minor choices, like how they designed a particular API or how they worded their documentation, could have a profound impact on how developers used or misused the system. It was all about anticipating potential pitfalls and trying to nudge developers towards those best practices that would ensure the overall reliability and scalability of the system.
It's like they were playing this constant game of chess, trying to anticipate the moves developers might make and designing the system in a way that encouraged those optimal strategies.
In a way, yes.
Yeah.
And they also learn the importance of constantly reflecting on their design choices and being open to refining them as they learned more about how the system was used in practice.
So it was a process of continuous improvement, adapting to the evolving needs of the users and the ever-changing landscape of Google's infrastructure.
Precisely. And they also highlight the importance of understanding those low-level technical details, even if you're working at a higher level of abstraction.
What do you mean by that? Why should developers care about those lower-level details?
Well, they give a great example of this with their discussion of using UDP for keep-alive messages because of TCP's behavior during network congestion. It was a reminder that sometimes those lower-level constraints can have ripple effects that impact your design decisions at a higher level.
So it's all about having that holistic understanding of the system and how all those pieces fit together.
Exactly. And they wrap up this section of the paper by sharing some specific examples of those unintended consequences and the lessons they learned along the way. They talk about the importance of careful API design, the need for comprehensive documentation, and that constant challenge of balancing flexibility with the need to prevent abuse.
It sounds like they really distilled those hard-won experiences into a set of valuable insights for anyone building distributed systems.
They did. And I think one of the most important takeaways from this paper is this idea that the design of a distributed system is as much about understanding human behavior as it is about technical elegance.
Yeah.
You have to anticipate how developers might use or misuse your system, and you need to design it in a way that encourages those best practices that will ensure its long-term success.
It's a reminder that even the most sophisticated systems are ultimately built by and for humans.
Absolutely. Now, they also emphasize the importance of reflecting on those past experiences, learning from both the successes and those inevitable missteps.
Right. It's all about embracing that iterative process of continuous improvement, constantly seeking ways to refine and adapt your system to meet those ever-changing demands.
Exactly. And they close with a rather intriguing observation about how their initial assumptions about the need for fine-grained locking turned out to be unfounded.
Oh, right. They had envisioned building a separate server to handle those short-lived fine-grained locks, but it turned out they never actually needed it.
Indeed. In practice, they found that developers often discovered that when they truly needed to optimize their applications, it often involved reducing communication overhead and simplifying their locking strategies.
So they solved the problem in a different way by streamlining their code and finding ways to use those coarser-grained locks more effectively.
Precisely. It's a great reminder that sometimes the most elegant solution is the one that removes complexity rather than adding another layer.
And that brings us to the end of this deep dive into Google's Chubby lock service. It's been a journey through the intricate details of a system that underpins so many of the services we rely on every day.
It has. And we've uncovered not just the technical nuts and bolts of Chubby, but also those valuable lessons learned about the challenges of building and operating distributed systems at Google scale.
From those clever patching mechanisms and those robust failover procedures to those unintended consequences and those surprising use cases, it's been a reminder that even the most sophisticated systems are a product of both human ingenuity and those hard-won experiences.
It's a testament to the power of thoughtful design and the importance of constantly learning and adapting to the ever-changing landscape of technology.
And as we wrap up this deep dive, it leaves us with a final thought to ponder. The Chubby story highlights how those seemingly small design decisions, those subtle choices made early on, can have these outsized impacts on the way a system is used or even misused. It makes you wonder what seemingly insignificant design decisions in the systems you use have had those ripple effects shaping the way they've evolved over time. Something to think about as you navigate the complex world of technology.
It's a reminder that the systems we build are not just static artifacts. They're living, breathing entities that shape and are shaped by the people who use them.
And with that, we conclude our deep dive into the fascinating world of Google's Chubby lock service.
We hope you've enjoyed this journey through the intricate details and those valuable lessons learned. Until next time, keep exploring, keep questioning, and keep diving deep into the world of technology.